We introduce HIFU embossment of acrylic sheets as an alternative technique to produce tailored embossed designs on acrylic without the need for traditional molds. Traditional embossing methods like injection molding and hot embossing require molds and precise heat and pressure control, limiting the thickness of materials they can process. HIFU embossment offers an alternative, handling various acrylic thicknesses without these constraints. We conducted extensive technical evaluations, performing experiments to illuminate the various parameters that affect the quality of embossment, such as embossment height, optical transparency, and line generation. The actual process of applying HIFU embossment to the acrylic was captured using a high-speed camera. The focal depth is 51 mm from the HIFU, and experiments are conducted with the HIFU vertically fixed in the water. The acrylic, which is transparent square shaped with 100 mm sides and 2 mm thick, is used consistently throughout the experiment. The acrylic plate is fixed to the XYZ plotter, and the experiment takes place while the acrylic is in motion. Transparency was controlled during the HIFU embossment. The left is white embossing, while the right is clear embossing. HIFU embossing can be applied not only to transparent acrylic, but also to acrylic of different colors and materials. HIFU embossing was used to apply to transparent blue, red, matte, black, mirror acrylics, and MDF. These results indicate that ultrasonic-based embossment is unaffected by the optical properties of the materials due to the nature of ultrasound not relying on light absorption or reflection. HIFU embossment can control the embossment height, optical transparency, and line generation. This is the results from measuring the embossment. The irradiation times were set at 1, 10, 50 seconds, respectively. It was found that greater embossment occurs when irradiation is done in front of the 51 mm focal point. However, a trend of embossment height increasing with longer irradiation times was not observed. This is the results of optical transparency measurement using a brightness meter. If the absolute transparency control is essential, the process should be done where the luminosity change is gradual and has minimal error, such as 8.90 VRMS or 28.7 VRMS with 10 or 50 seconds irradiation time, and before the focal point. This indicates that the speed at which the acrylic is processed could have significant effect on the resultant embossment, but exposing the acrylics longer than 10 seconds does not substantially change the outcome. We investigate line generation under varying conditions. Measured diameter of embossment at the condition of 8.90 VRMS, and the maximum line thickness was 1.48 mm at the distance of 51 mm. At 17.8 VRMS, the maximum line thickness was 4.41 mm at the distance of 46.5 mm. At 26.7 VRMS, the maximum line thickness was 6.19 mm when the distance was 42.75 mm. We conducted a workshop at an international conference. We collected feedback from 70 participants. During the workshop, users had the chance to emboss acrylic manually in the water. As a result, 80% found the procedure intuitive. Approximately 20% pointed out the challenge of maintaining the focal point of the HIFU. This shows the participants manually processing acrylic. The participants who created the top 3 mentioned, it was easy to process with HIFU embossment, while those who made the bottom 3 gave feedback saying, it was difficult to process with HIFU embossment. Through the workshop, it was identified that computational control over the HIFU embossment is an essential to consistently achieve the desired outcome. We developed a web-based drawing application and utilizes a robotic arm for executing HIFU drawings on acrylic. The application is built using Python and Flask. The robot arm was placed on a fixed optical breadboard situated atop a large water tank. The robot arm housed a custom 3D printed holder to secure the acrylic in place. The user draws what they want on a canvas located on the web application. The user could choose between clear and white line and also between thin and thick lines. A camera mounted above the acrylic holder allowed users to monitor the drawing progress in real time. Since the robot continuously moves the acrylic, the irradiation time depends on how quickly the robot moves the acrylic across the HIFU focal point. The HIFU irradiation patterns were signaled to the HIFU and the robot arm moved the acrylic in accordance with the user's specification. The effectiveness of this user interface was evaluated through a user study involving 19 participants. The images are illustrations by participants, drawn without specific guidelines on what to create or how to adjust the parameters. Upon analyzing the quantitative data gathered from the 19 participants' responses in the questionnaires, we observed a positive perception of the HIFU-based drawing method. As a result of quantitative and qualitative evaluations, Our findings accentuate the potential of HIFU embossment as a versatile and precise approach for accessibility, personal embossing fabrication, and various artistic applications. We plan to refine our understanding of the HIFU embossment, expanding its applications, and increasing the fidelity of embossed designs. Continuous research will focus on optimizing the parameterization of HIFU to create more consistent and detailed embossing that can be reliably replicated, facilitating tactile experiences and interactions in the realm of personal fabrication and beyond.